Well, it's not an easy topic, but I'll try to make it as simple as possible. So let me give you the first definition. The inverse function of the exponential function f of x equals to a to the x is called a logarithm, and it's denoted as log base a of x. That's the definition. And this definition is extremely hard because a lot of times when people ask what's an inverse function, it's hard to explain. But my students, you guys know how to explain inverse functions, right? How do you explain inverse functions?
So like opposite of the regular function?
Well, that's disappointing. If you're my student, you should be immediately invoking what?
Oh, the chickens.
Chickens and
Oh, yeah.
Oh yeah,
It's the
chicken nuggets.
going into
Right. So if somebody asks you what's an inverse function, how do you answer? A function is like a factory where it takes in an input and it gives you an output.
Right.
Except that the output has to be consistent, right? For the same input, it has to always give you the same output. Okay? And then an inverse function is like the inverse factory where you do the opposite of the original factory. So for example, let's say you have a factory which takes in the chicken and gives you back chicken nuggets. What's the inverse factory? It's an inverse factory where it takes in chicken nuggets and gives you back chickens. Okay. That's what an inverse function is. Alright, good? Plenty easy, right? Alright, so now let's see what the consequence of that is. Let's think about f of x equals to 2 to the x and the inverse function which is denoted as log 2 of x. Okay. So this weird symbolism was invented by John Napier in the 17th century. So, and it stuck. If you don't like this and you think there's a better way to write down the inverse function, that would be nice, but it's too late to change it. So we're stuck with this notation for the inverse function. But let me see. If I have f of 3, what's this value? What's f of 3? 2 to the third power, which is
8.
2 times 2 times 2 is 8, right? Then we know that f inverse of what is what?
F inverse of 3 is log 3a. Oh, no,
Log
log
2.
2, 3.
Log
No. This is chicken nuggets. So what do you put in here? Yeah, so what do you put in here? 8. You put in 8.
Oh.
And that should give you what?
Log 3.
3. No. You put in 8. If you put in 3 and you got 8, then you must put in 8 and you get 3.
Oh.
Well, what is f inverse of 8? That's log 2 of 8, right? So this is this. That's how you think about it. Right? Okay. So now f of 4 is 2 to the 4th power, which is 2 times 2 times 2 times 2, which is 16. Therefore, f inverse of 16 must be 4. And therefore, we know that log base 2 of 16 is 4. That's what we know. Okay. In addition to this, let's think about the graph of the function. The graph of a to the x is something that we've been working on last week, right? The graph of y equals to a to the x is like this one where, what's this point? 0, 1, yes. So the y-intercept is 1. For any value of a that's bigger than 1, you always have this shape of the graph. Okay? Now, if you drew the graph of y equals to log base a of x, that's the inverse function of this, right? How does the inverse function graph look? It's a reflection over? No. Here's x and here's y, and you're switching input and output, right? If you switch these two around, what happens? It flips over what?
Order.
The diagonal. Flips over the diagonal. Okay? See, if x and y are switched, it flips over the diagonal, which is y equals to x. Okay? So what does that give you? That. Which is this. Okay? So that's the graph of y equals to log a of x. Okay, so this first definition should give you some feel for what the log is. It tells you that since the graph of the inverse function is a reflection over y equals to x, this should be the shape of the graph that we were talking about. This is the function. And we know some values by just inverting the known values, right? But this definition is not so easy to work with, and that's why we'll have to work a little bit harder to come up with the second definition. And if you accept that second definition, it'll be a lot easier. So let's work on that one. So first thing that you should know is that there's an identity that holds true for any inverse functions, which is that if you compose the inverse function in itself, they kind of cancel. See, f and f inverse, if they're composed, they just cancel out. Now, why is that true? Again, you can talk in terms of chicken and chicken nuggets. So, if you had, let's look at this first one. So, let's say x is the chicken, then f of x will be
Chicken nuggets.
chicken nuggets. But if you plug in chicken nuggets into f inverse, what would you get?
Chickens.
You get the original chicken back. Make sense? Right?
Yeah.
So what you started with, you're going to get back because you've composed f with f inverse. Is that good?
Yes.
Now what if we have this one? Let's say x is a chicken nugget. Chicken nugget fed into inverse chicken nugget factory. What does that produce?
Chicken.
Chicken. And then now you take that chicken and feed it into the original factory, you get
Chicken nuggets.
chicken nuggets. Right? So you started with chicken nuggets, so you got back your chicken nuggets. Yeah. Something happened in between, we don't care, some magic happened, but you got the same exact thing. Okay, so you can kind of see that if you compose the inverse function with itself, they're going to cancel away, right? Now, not only this is true, but you can think of this as a property of an inverse function, as a defining property of an inverse function, because there's some kind of a theorem that you would learn if you're a math major, and if it's in your first proof class, you get to prove the following fact. So the fact is that if g of x satisfies f of g of x equals to x and g of f of x equals to x, then g of x has to be the inverse function of x. Okay? So that's some kind of a fact that you learn as a math major. But this is just written for something who might question further, deeper into what I'm doing, but at the end of the day, what I'm trying to say is that if you plug in this function into this function, you get the original x back, and vice versa. If you plug this into here, you get the original function. And because of this fact, you can just say that that's a defining property of the log function. So let me try to write down the second definition inspired by the fact that inverse function and the original function cancel each other. So if I take a to the x and log base a of x, and you plug one into the other, so let's start with this one. If I take this one and plug it in here, so you take this, erase this x and put this in here, so you have log a of x. Then what I've done is I plugged in the inverse function into the original function. What happens then? what happens if you plug in the inverse function and the original function? You get your original x. You get your what you started with, because they can't. The original function and the inverse function cancel each other. Let me write this bigger, because this is going to be a very important definition. Okay, so I'm going to say definition 2. A of log base A of x is x. Okay, so that's one rule. Number 2, you can do the other. You can take a to the x and plug it in here, replacing this x. So see, log a of x, you raise that x, and into that x you plug in a to the x. Okay, if you do that, what do you get back? Your x back, right? And these two rules are just cancellation laws. It just means that these two cancel and these two cancel. And by some mathematical theorem, it says any function, so we can take this as the definition of the log. If there's any function that satisfies these two kind of cancellation laws, that's equivalent to saying that it's an inverse function. So we can, once we have this, we can basically forget about everything that we learned so far. All of this is irrelevant. We don't have to remember. Erase. And you can just simply take that as the starting point. Okay? Okay. Well, maybe you're not going to be sold yet because it still looks complicated, but let me sell you another idea. I believe that you know something if you can compute it. So for example, if you know how to multiply two numbers, then you know multiplication. You know what it means. Do you agree?
Yes.
Well, maybe you still lack some concepts, like multiplication really means like you can make the same number of dots in a two-dimensional way, and you're counting everything. Stuff like that. You might be lacking that, but you still can memorize the multiplication table and do the computation. How about this? If you know how to add two numbers, then you know what addition is. Do you agree with that statement? Okay.
Like any two numbers, or only like if I
Like
only know how to add
okay,
one-
some integers, some
Okay,
yeah,
yeah.
okay, yeah, okay, all right. So the reason I'm saying this is we're just going to compute some numbers, and if you can compute these logs, slowly you're going to see that, oh, I know logs. That's the idea, right? So let's start doing this. Okay? So compute a log base 2 of 8. Well, we want to write in this format, so we want to rewrite the 8 as 2 to some power. Okay? So 8 is 2 to what power? Third power. So what? Now what can you do? What's the rule? Cancel. So what's the answer? Huh. It's the same result as we got before. Right? But we didn't have to think about all these inverse functions. All we had to remember is the cancellation law. We were able to compute it successfully. Right? Okay, let's try another one. Log base 2 of 16. Okay, 16 is 2 to what power? Fourth power. So what's the answer? Awesome. Yeah, same result as before. Okay. So what's happening is, like, we didn't have to use the very first definition of being inverses. All we had to do was just accept this new definition, forget everything before. This is all you know about logs. Okay. If somebody asks, what's a log? Just say, oh, it's an inverse function of the exponential function. And if they press, what does that mean? Then you reply, well, you can forget about what I just said. Just write these two rules. These are the only things that you need to know for logs. Okay? Yes?
So all of those are asking is whatever the base is? whatever, so find the exponent,
That's what it is. That's what log is, right?
so find the exponent
Yeah,
of the base to give you.
Yeah, if you think about it, that's exactly what it needs to be the inverse function of the exponential function. But that, when you think in that way, there are too many words there. It's harder to think. It's easier to just look at something and cancel. The cancellation makes the brain happy for some reason. It makes things simpler. We like it, okay? So if you accept that as the definition, then suddenly logs become a lot easier to grasp, okay? All right, so let's do another one. What will this be? Okay, square root is what power?
1/2.
1/2 power. So what's the answer? Okay. D. What if you have log base 2 of 1/4? Okay, this requires a bit more work. First, 4 is 2 to what power? Second power. But here's something that you have to watch out. You can't cancel these two because they are not in this form. Okay, only when it's strictly in this form you're allowed to cancel. In fact, this is somewhat dangerous way to teach logs. How many of you were taught log this way? Probably nobody. Only I do it this way because it's usually considered dangerous because people are so happy. Like, it's just like if you give a child a gun, they'll just shoot whatever, right? Yeah. So it's like it's so dangerous, right? Yeah. Should I do it?
Just throw them straight to a gun?
Well, everyone woke up at least. Okay, good. So, okay. I'm somewhat surprised at my own comment. Okay. Well, anyways, the thing is, you shouldn't be cancel happy. That's my point. Okay. You shouldn't cancel just because you see the same number, because you can only cancel if it's exactly the same format. Log base a and a to some power. This 1 over this extra part makes it not the same as this. Okay, so how do you write? The real question is, how do you write this 1 over 2 squared as 2 to some power? What goes in there? Negative 2 power. Yes, negative 2 power. So negative 2 power goes here, and now what can you do? Now you can cancel. All right. Okay, let's try this. First of all, you have to make everything powers of 2, right? So 8 is 2 to what power? 3. Third power, right? And then what cube root should always be changed to? 1/3. 1/3 power, and 4 is 2 squared. Right? So I'm rewriting 4 as 2 squared, rewriting cube root as 1/3, and 8 as 2 to the 3rd power. Yes?
What did you say the answer was?
We'll see. Okay. So now it's going to be 2 to the 3rd times. What do you do if you have two numbers like this? You multiply it, right? So you multiply that, and you get 2 to the 2 times. What's 2 times 1/3? 2 over 3. Okay, but then what do you do when you have the same base and when you multiply? The exponents add, right? So you have log 2 of 2 to 3 plus 2/3. And by the way, again, it's very important that you don't cancel too early. So these two shouldn't be canceled because there are other things, okay? Only when you have log 2 with 2 to the something you can cancel. So in fact, right now it's safe to cancel. You can see this is in fact log 2 of 2 to something, so you can cancel these two. But let's hold on a little bit more. Rewrite 3 as what? 9 over 3, right? So you can rewrite this as log 2 of 2 to the 9 over 3 plus 2 over 3. And if you add, that's 11 over 3. So you have log 2 of 2 to the 11 over 3. And now you can cancel. Well, you could have canceled over here and then did 3 plus 2/3. Actually, that may have been shorter. Okay, well, anyways, that's how you do it. Okay. Now, let's think about f log base 4 of 2. What do you think this is? Yes?
Why does log 2 and just 2 cancel?
Why do these two cancel?
Yeah.
Oh, because that's our definition.
Oh, okay.
Yeah, if you have this and this, they cancel. I'm working with a different definition of logs, which is equivalent to what every other professor teaches. Okay, okay, what's log 4 of 2?
1/2.
Why is it 1/2?
Because the exponent on 2 to get 4 will be 1/2.
Right, so because 2 is square root of 4, right? And then if you think about it, square root is 4 to 1/2 power, and they cancel, you get 1/2. Is that okay? Is that good?
Yeah.
Alright. Okay, now let's do, I don't have any more room, so let me write over here. G, what if you have log base 27 of 9? That's trickier than anything that you've done so far. So one thing that you should know is that 27 is 3 to what power?
3 to the 5th.
What? No.
3 to the 3rd.
3/3. Right? 3 times 3 times 3 gives you 27, right? And 9 is 3 squared, right? So it's a bit hard to think, but what you want to do is you want to rewrite 3 as cube root of 27, or 1/3 of 1/3 power. Okay? Cube root of 27 is 3. You agree, right? Yeah. But cube root is the same as 1/3 power, so that's what I'm going to do. I'm going to rewrite this as log base 27 of 3 squared. 3 times 3 is 9, right? So write it as 3 squared. But then I'm going to rewrite 3 as 27 to the 1/3 power, and then there's a squared. Okay. All right, what's the rule? If you have a 1/3 and a 2, you multiply. So what do you get? Log 27 of 27 to the what power? 2/3. And after canceling, you get 2/3. Okay, so I'll give you more examples for you to try, but already you should be thinking of two things. Okay, one is like, hey, I can actually calculate this, so I must know logs. I must know what log is, okay? But at the same time, some of these questions are too hard. I wish there was something simpler, okay? So I'm going to write down the log rules to help us. Log rules. Okay. And the first one is log AXY is equal to log A times X plus log A of Y. Second one is log A of X over Y is equal to log A of X minus log A of Y. And these two rules, I like to call them log splitting rules. Because if you look at what it's saying is that if you have a multiplication inside the log, right, there's a multiplication between these two, right? Then I can split that single log into two pieces of log with an addition. That's what the first rule is saying, right? And the second rule is saying that if you have a division inside the log, then you can split this single log into two pieces of log with a minus between them. That's what this rule, second rule is saying. Okay, so that's what I call log splitting rule. C, log base a of x to the cth power is same as c times log a of x. Oh, by the way, this is my own terminology. It's just this is not the official name for these rules. It just makes the rule a little easier to comprehend. Okay. Now, for a long time, I didn't have a nice name for this one. But then, when my son was 4 years old, I was reading him a picture book at home, and the picture book said, "The frog jumped over the log." It rhymes, right? And I immediately knew this is what I need to use in my class. So from then on, I started calling this one as the frog over the log rule. Okay? Frog over the log rule. Why do I call that? Well, this c, the exponent inside the log, it jumps over the log like a frog. Yeah, right? And then c can also jump back over to be here. So there are two spots where the frog likes to be at. Okay, and in both cases, to go into one spot to the other, you have to jump over the log. So that's why I call this a frog over the log rule. Okay? Right. And then D, log base A of 1 is 0. Often this is not a separate rule, but since so many people forget about this, I just write that as a separate rule. And then E, there's something called the base change formula. And by the way, these other ones are my terminology that I coined. The base change formula is the official name for the following identity, that log base A of B is equal to log base C of B over log base C of A. Okay. My point is that these rules can be employed to find answers more easily. So let me read some of the previous questions and give you a demonstration. So if you have log base 2 of 8 times cube root of 4, well, this is a multiplication, right? So if you have multiplication inside the log, what can you do? What does the rule say?
You can add it.
You can split the log, right? And then put an addition between them, right? Okay. So you can rewrite this as 2 logs and put an addition between them. Now, I don't like saying just you can add, because a lot of times that's the way people read this, and they have a major misunderstanding that suddenly you were taught to how to do multiplication and addition, and you knew that these are very different ever since high school, ever since childhood, and then at some point you learn logs, and now they seem to say, oh, multiplication is the same as addition. It's ridiculous, right? No, that's not what this rule is saying. It's saying that multiplication can be split into 2 logs. That's the point. 1 log becomes 2 logs. That's the point, okay? And then you place a plus in between. Do you have a question?
No, I answered it.
Okay, all right. All right, and then now what do? You have 8 is 2 to what power? 3rd power, plus 4 is 2 squared, cube root is 1/3 power. These cancel, that's going to be 3. Log 2, these two multiplies, so it's 2 times 2 to the 2/3 power. And then you rewrite 3 as 9 over 3, and you cancel this, put it as 2/3. That's going to be equal to 11 over 3. So we basically have solved the same question in a slightly different way. I guess the amount of complexity is about the same, but you know, just the fact that you can like get rid of these log early on kind of gives you more comfort, I think. Okay, so I would say this solution is slightly better than this one. Do you agree? Okay, all right. Now, what about this challenging one that we did? Okay, so let me move on to this G. So if we redo log base 27 of 9, well, I think this base change formula is the hardest one to grasp because this C comes out of nowhere. You don't have this C on the left side, and this C comes out of nowhere. And it's really the thing that makes application of the base change formula easy because you're allowed to choose whatever C you want. And if you look at 9 and 27, what's common about them? 3, because 9 is 3 squared and 27 is 3 cubed. So what you want to do is you want to choose C as 3. So if you choose C as 3, B as 9, and A as 27, okay, what goes in here? Look at the formula. Log base what? 3. And what goes here? 9, okay. Over here, base 3, and then 27. That's what it means, right? Yeah, so with these numbers, I apply the base change formula, and I got this identity. But 9 is 3 squared, and 27 is 3 to the 3rd power. And now we can cancel these, you can cancel these, and you get 2/3. Done. And that's a lot easier to think than trying it out this way. This was a major challenge if you think about it, right? It's not as easy to think, but that helps you greatly, okay? So that's why these rules are useful. You should know these identities, and you have to know how to use them. But then, rather than just giving you examples of how to use them, I want to spend some time proving them today. Now, why am I trying to prove these identities? Not because I want to put them on the exam. You'll never be asked to prove them on the exam, okay? However, instead of asking you to prove it, we're just going to review it, and once you see the proof, then it'll just make sense. It kind of, seeing the proofs helps you understand why some things are happening, okay? So, try your best to understand the proof. You'll definitely have a better understanding of these rules, okay? So let's prove each one of them. Okay, let me prove the first identity. I want to start off by rewriting this as log base A of A to the log base A of x times a to the log base a of y. Why are they the same? Why are these two same? Can anyone explain?
Because the A and the log A cancel out.
Which log a?
The one
This
that-
log a or
No, the other one.
this one, right? Okay, so these two,
They cancel out.
I erased the definition, but remember, the definition of the log is that it satisfies two cancellation laws. They cancel like this, and also these cancel like that. These are the two cancellation laws, which is the fundamental property of logs. Okay? Accepting this will enable you to prove anything about logs. Okay? So if you took this one and canceled these two, you get x. If you took these two and canceled, then you get y. As usual, when I ask you to verify an identity, you don't go this way, you go backwards. That's easier. Okay? Yeah. Okay, so are you with me? You see that this is just a complicated way of writing this. Okay? But it just has to become worse before it gets better, because now I'm going to apply something. If you have the same base and you're multiplying, what do we know?
They're gonna, they feel like added together.
What's added together?
The x and the y.
The exponents are
Yeah,
added together. Okay?
right.
The exponents are added together. Okay, so log a of a to the log base a of x, which is the exponent of the first one, and log base a of y, which is the exponent of the second one, they should be added together. Okay? Now look, what are we trying to prove? We're trying to prove these two. The identity that these two are equal. Okay, we are almost there. What can we do? How do we finish the proof? Almost done. Cross out which ones?
Log A.
Done. Proved. One line proof. Yeah, it's a lot simpler than you think. Right? Right. So not only it's not hard to understand why this does work, but you gain some understanding. See, you have the exponential rule that multiplication between two exponents of the same base, you write the base only once, unchanged, and you just add the exponent. That's the rule in the exponential world, right? But because logarithm is the inverse function of the exponential function, that rule has a counterpart in the logarithmic world. So, you know, in these Marvel Universe movies, there are like parallel universes, and there are like different, say, what was it? Doctor Strange in this world and another world, right?
Mhm.
And they're slightly different, but they have some kind of parallels, right? It's just like that. You have the exponential world and the logarithmic world, and if you have rules in the exponential world, there's some kind of counterpart in the log world. And that's what you're seeing. You're witnessing that counterpart. Okay? In this multiverse of logs, you see that exponential rule has been changed into this first rule. Good? All right, so let's move on to the next one. You'll probably be able to prove this next one on your own. So you may try that. Okay. Okay, what should I do? Replace x by? Make it look really complicated, right? Yeah. That's a really complicated way to write x, but that's same as x, right? Okay. How do you write y? A to the log base a of y. Right? Okay. Now what? If you have exponents with the same base, and when you divide, what happens to the exponents? Subtract, right? So you have log base a of a to the log base a of x minus log base a of y. And then how do you finish the proof?
Cross out.
Done. So we've proved part B. Okay, let's prove C. All one-liners, very, very simple. Right? Log base a of x to the c. Again, write x in a really complicated way. Just like that. But then, when you have an exponent inside, parenthesis and another exponent, what's the rule? In other words, what's the rule for this one? A to the m to the n. What's that? You multiply, right? So we just have to multiply these two. But since multiplication is commutative, let me write, instead of this times this, I'll write c times log ax, okay? I just want to make the end result look like that. So I'm just going to write c first and then log ax. All right, so I'm going to write log a to c times log ax. And now what? What's the next step?
Cross out.
Cross out log a and a. You're done. You're on a roll. We're just proving every one of these identities. Okay? Yeah. These identities that seem to come out of nowhere actually has a reason. We're just working in the parallel universe. Okay, and then log a of 1. Okay, 1 is a to what power? Anything to what power is 1? 0th power is 1, right? So anything to 0th power is 1. So you can rewrite 1 as a to 0th power. But then what is this?
Cancel out the a and the log.
Okay. Okay, so you can prove these things. Now, E is a bit more involved, so it doesn't really benefit yourself to prove this, but nonetheless, let me just show you a proof of E. And if you're writing notes, you don't even have to take notes of this. This doesn't really tell you much. So what you do is you say log A of B times log C of A. You start with this, okay? And then you treat this like the number in front of the log. So this entire thing will be like a frog, which will jump over the log, right? And then it's going to lodge right here, right? So this is going to be equal to log base C of A of log A of B. Okay? Now what can you do? You can cancel these two, right? So now that allows you to say that log A of B times log base C of A is log base C of B. Okay. How do you get the identity that we were trying to prove from here? This is equivalent, right? How do you get that identity from here? We're trying to know what this is, right? So you divide this out. So the answer is log base A of B. If you divide this to the other side, you get log base C of B over log base C of A. So that's the proof, but this proof is not really adding anything, because first of all, it's not really from the parallel universe, the exponential world. So it's something that's unique to the logs. I don't see a parallel law in the exponential world. But let me try to explain the more important side of the base change formula. So let me write a few notes. Note, on your calculator, if you're using a scientific calculator, there is no log A of B. So you have to know how to calculate this using your calculator. And the way you do it is you rewrite this as ln of B over ln of A. That's because a lot of calculators do not have, most calculators that I know of do not have this function. Maybe there's hidden in some menu, but it's hard to see. Okay? So let's say you're trying to solve this question that we solved earlier using your calculator, and you try to look for how to put this into your calculator, you can't find it, okay? And then during the exam you raise your hand and you say, Professor, can you help me with putting this into the calculator? And my answer would be,
No.
no, I ain't going to help you.
No,
Right?
no.
Yeah, I'm not going to help you with that, right? You'll have to know, okay? And the way you do it will be, you use the ln function, put it as 9, and ln as 27. That's how you're going to do it. Okay. Now, why am I saying this suddenly out of nowhere? I'm saying this because this is what this base change formula is doing. Okay, so this ln of x really is what we write as ln of x. Okay, and this is called the natural log. Let me write it down. Natural log. Natural log is log base e of x. You know this e that we briefly talked about last time? E is 2.71828. It has this special property having something to do with the slope of the graph. Yeah, so that special number, because it's so important, a log that has this number as base is called ln of x. And the reason that that's so important is because when you get to calculus, this is a lot easier to differentiate than, say, log base 2. Okay, so this is for somebody who have seen derivatives. I doubt you did, but this would be log base 2 of x over ln of 2. Something like this. Whereas if you differentiate log ln of x, it's just simply 1 over x. Oh, sorry, it's 1 over x times ln of x. So this is a lot harder to work with if you go to calculus than this one. So that's why they have this special thing. Of course, you don't have to know this. Don't even write this in your notes. Well, anyways, that's called natural log. And what we're doing is we're just taking the base change formula log A of B, and we're using C as E. If you write the base change formula this way, then since log E is ln, this really says that ln of B over ln of A is what log A of B is. Okay? Right. So you could have gotten the same answer 2/3 by doing the following. You just take ln of 9 with your scientific calculator, divided by ln of 27 with your scientific calculator. And if you do that, you're going to get 0.6666, something like 6, and then 7, right? And then, not all calculators can do this, but a lot of times they have this fraction to decimals. If you do second and then this one, it converts this into 2/3 and you get the answer. So that's how you can get the same answer using a calculator. And since I'm talking about this, let me add another log. There's something called a common log. This is written as capital LOG of x. If you see LOG without any base, nothing in here, that really means log base 10 of x. Okay. And when John Napier first developed logs, this was the log table that he worked with mainly, because it helped to cut down calculation time for huge numbers. So back then, astronomy was really in revival. People were like looking at the stars and trying to figure out their motions and stuff. And they had to multiply or divide or add with some really big numbers. And John Napier realized if you have a log table, you can reduce the time by, like, you can make it 4 times faster or something. Nowadays, it's not as important because computers can do everything without having the need for logs. But back then, this was the historical reason why people were doing logs. Okay? So that log also is in your calculator. So if instead of taking base e, if you take this base change formula and use base 10 instead of base c, then you can write log 10 of b over log 10 of a. Okay? And that is really capital LOG of b divided by capital LOG of a. Okay. So I'm giving you 2 solutions on how to use your calculator to calculate the logs. Okay? If you have to calculate log a of b, you can either divide log b divided by log a, or ln of b divided by ln of a. Okay? And these formulas are something that I will never ever tell you during the exam, so you should better know it now. Okay? All right.